Students, on this video, I'd like to examine 5 examples which will help you learn to solve inequalities. I've got regular inequalities, quadratic inequalities, and I'd like to include especially an example that shows you what to do with a 3-part equation. Let's take a look now at all 5 examples. Let's take a look at our first equation. I'm going to isolate the x exactly the same way I would if this were an equality instead of an inequality. First of all, there is only one x, so on the side with the x, let's eliminate the term without the x, just as we would in a basic equality equation. Let's go ahead and subtract 7 from both sides of my equation. On the right side, that leaves me with just 4x. On the left side. On the right side, I have 4. Now again, I'm solving for x, so what I'm going to do in this case is divide both sides by 4. And that leaves me with x is greater than or equal to 1. Now let's go ahead and graph it. First of all, I'm going to put a point at 1. And in this case, I will put in a filled in point. I want the values that are greater than 1, so we will go in this direction. And there's my solution set graphically stated. Now, I could state it as well in interval notation by saying all the numbers, including 1, all the way to infinity. Now, let's check our answer regardless to make sure we're correct. It's always my opinion that the easiest thing to check is a 0. Now, frankly, what most students would prefer doing is to go and put in a 2. But the arithmetic's a little harder with a 2, albeit not too terribly hard. It's always easier with a 0. If I go back to my original equation, you'll notice that the 4x, when you plug in a 0, becomes 0 plus 7. The terms with x literally just disappear when you have a 0. 0. Is that greater than or equal to 11? Of course not. But don't forget, 0 is not supposed to be part of my answer set. So in this case, I must have the arrow going in the correct direction. Now, let's also be sure that the 1 is the correct place where my graph is to be equal to 1. In other words, there's 2 things I have to check: the equality and the inequality. I need to be sure that the value is that this comes out to be equal to 11 when x is 1. If I put in a 1, I have 4 times 1 is 4, plus 7 does indeed equal 11. So my filled in dot is at the correct place, my starting point is at x equals 1, and the values where it is greater than 1 go to the right. Now I'd like to show you, I could have solved this thing exactly the same way, literally going ahead and just making it an equality to begin with. I would solve it exactly the same way, subtract 7 from both sides, divide both sides of my equation by 4, and come up with the exact same answer. Again, it would nearly be necessary for me to check with my 0 to see if I had the inequality correctly placed as well. In other words, was the arrow going in the right direction? So if you prefer, you can always just write it as an equality, the equations we've been solving prior to this section, and work it through, and then just check to see which direction the arrow should go. Let's take a look at our second example. This one's a little bit more complicated, and there's a couple little things I want you to see as I go through it as well. First of all, to solve it, I'm going to have to multiply through both sets of parentheses and do some simplification. When I multiply through, I have 2x minus 4. When I take my negative through the parenthesis, the easy thing to do is to realize, again, as I mentioned on the last video, when you take a negative and you put it in front of another variable, it changes the sign. So my positive 3 became negative, and my negative 7 became positive. If you prefer, however, you can think of this as a 1 sitting in front of the parenthesis, and literally distribute the negative 1 through the entire parenthesis. Don't forget, and what students too often do, is to take the negative all the way through the parentheses. Don't change just the first sign. Okay, continuing on, I need to combine my like terms, so I have positive 2x's, take away 3x's, leaves me with 1x. And finally, I have negative 4 plus 7 is positive 3. Again, I need to isolate my x, so I'm going to subtract 3 from both sides of my equation, and that'll leave me with negative x is greater than or equal to 1. Now, in order to solve that, I can do a variety of things. I can multiply through by negative 1, or I can divide through by negative 1, but the point is I need to get rid of that negative in front of the x. It's up to you, but I think most students actually think of this as the negative 1 sitting in front of the x, and then dividing both sides by the negative 1. Now, something has to happen here. When I divide by a negative, I cannot leave this sign the same way. Remember, whenever you divide or multiply by a negative, you switch the signs, and you therefore switch the relationship. So this sign actually needs to be flipped over. I need to, at this point, actually say that x is less than or equal to negative 1. Now let's go ahead and graph the solution. At negative 1, once again, I'm going to have a point where I believe it's equal to negative 1. Actually, let's go ahead and check that answer real quickly here in our very basic equation, our very original equation. Negative 1 plus 2 would give me negative 1 minus 2 would be negative 3, times 2 would be negative 6. Inside this parenthesis, I would have 3 times negative 1 is negative 3, minus 7 would be negative 10. But notice, I now have negative 10, which is really positive 10, and negative 6 plus 10 does indeed equal 4. So I indeed have my dot, my filled in dot, notice, at the correct spot, negative 1. The equality checks. Now, where are the values of x less than negative 1? Of course, the less than values would be in this direction. Once again, I'm going to use the value of 0 to check. Now 0 is on the right side. It should not work in my original equation, and this is easy to verify. And remember, the reason that I like to use the 0 to check is the x's essentially disappear. 0 minus 2 is simply minus 2. 2 times negative 2 would give me negative 4. If I take my 0 through here, again, that disappears because 3 times 0 is 0, and negative 7 is plus 7. Negative 4 plus 7 gives me a positive 3, which is indeed not greater than 4. So 0 should not be included, and if you'll look back at our graph, 0 wasn't included in the graph, so my arrow is going in the correct direction, and this is the solution. Now, I'd like you to notice one other possibility, by the way, where you don't have to worry about flipping the sign. Let's look at my equation right here, where I had negative x is greater than or equal to positive 1. One way to get around this and never have to worry about flipping the sign, which means you'd never multiply or divide by negative 1, would be to add the x to both sides in order to essentially make the x into a positive without multiplying or dividing by a negative number. On the left side, these cancel, so I'm left with 0 or nothing when you're adding and subtracting. On the right side, I'll go ahead and put it in descending order and make that x plus 1. Now to isolate x, again, I'll subtract 1 from both sides. And to get the same solution again, negative 1 is greater than or equal to x. Now I want you to notice that in both cases the arrow is pointing at the x. In both cases then, even though these equations look different, we're saying that the x is the thing that is smaller than the negative 1. So both solutions, even though they look different, really are identical. Finally, let's look at the graph and talk about how we could write this in interval notation. You'll notice that all my values were, again, the values equal to or less than negative 1. On this end, I could go down to, but not including, remember, negative infinity. You can never be equal to infinity, so you'll always have a parenthesis whenever there's an infinity. All the way up to and including negative 1. So there's the interval notation way to give the solution to this problem. Let's look at our third example. Notice this time I've got a quadratic equation. Now, in the case of a quadratic equation, you absolutely want to set it equal to 0. That's true whether you're doing an inequality or an equality. The first thing is to determine the point or points where the equation is equal to 0. So in this case, I'm going to subtract 3 from both sides, which will leave me with a 0 over there on the right. Now I have a trinomial that is easily factored. And notice in this case I have the product of two binomials that are equal to 0. And again, I'm ignoring the greater than for just the moment because my first priority is to determine whether they're equal to 0. If they're equal to 0 and it's this times this, that automatically tells you that one of these binomials must itself be equal to 0. So either x minus 3 must equal 0 or x plus 1 must equal 0. Now to solve, I merely add 3 to both sides of this equation, which gives me x equals 3. And of course I would subtract 1 from both sides of this equation, which would give me x equals negative 1. Now you should check these to be sure. Let's go back to my original equation and let's try the 3 first. 3 squared is 9, minus 2 times 3 is 6, and 9 minus 6 does indeed equal 3. If I try the negative 1 squared equals positive 1. Negative 2 times negative 1 equals, negative 2 times negative 1 equals positive 2. And positive 1 plus 2, again, does equal 3. So these are the two possible solutions. And you'll recall we knew there were two possible solutions because of the exponent, where the situation where these are equal to 0. So this equation would be equal to 0 at either x equals 3 or x equals negative 1. So in this case, let's go ahead and realize that we're going to have a dot at negative 1 and positive 3. Now I'm going to fill those dots in again because I know equal to is included again. Now, what I need to do is determine which of these three zones make this equation true. Now, there's a lot of ways to do this. Number one, I could just plug in a value, say 4, and I could determine if it makes this equation true. If it did, then I would include this region of the graph. For example, 4 squared would be 16, minus 2 times 4 would be 8, and indeed 16 minus 8, or 8, is indeed greater than 3. So I know that the arrow would indeed include all of this. I could plug in a 0. I love 0 because, again, all the x terms disappear, so I'd have nothing. So 0 is not greater than 3, so this middle region would not be included. Finally, I could pick a value below negative 1, say negative 2, plug it in. Negative 2 squared is 4, minus 2 times 2 is 4, and again I'd have 8 is greater than 3, which does work, which means this third zone would be included. Now truthfully, that's an awful lot of work. An easier, shorter method to do this is to look at each one of these binomials individually. First of all, let's look at the x minus 3. We know that this is equal to 0 whenever x equals 3. If x is bigger than 3, in other words, to the right of 3, my value will give me a positive number. For example, 4 minus 3 is positive 1, 5 minus 3 is positive 2, etc. As far as you want to go to infinity, those will all be positive. At 3 is where it's equal to, of course, exactly 0. And anything lower than 3 is where it's a negative. And again, if you want to try a 2, for example, 2 minus 3 is negative 1. That's a negative value. 0 minus 3 would be negative 3, etc., etc., etc. So any value below 3 for just this binomial would result in a negative value. Let's take a look at x plus 1. I know that it's equal to 0 right here at negative 1. I also know that to the right of that value, say 0 for instance, 0 plus 1 would be positive 1. Any value to the right is going to give me values that are greater than 0, of course, or positive values, all the way to infinity if I wish to go that far. To the left of 0 again, say negative 2 plus 1 would be negative 1. But again, to the left of 0, of course, will be all my negative values. Now, what I want you to notice is that your two values, your two binomials, when you're over here in the far right section, they're both positive. A positive times a positive would give me a positive, which of course is greater than 0. So all of these values over here would be included. And I'll go ahead and graph it now. Let's look at the middle section. I've got one of my binomials as a negative, the other one's a positive. If I take a negative times a positive, that would be a negative. And of course, negative numbers are not greater than 0, so this would not be included. Finally, on the bottom side, I have all negative values, a negative times a negative in this case. So in this case, two negatives is an even number and does yield me a positive, which again is the values I'm looking for. So these are the ones that are greater than 0. Now, what I'd like you to see in my ideal world, that if you go far enough past your last critical point, the last point where you're dividing positives from negatives, if you're way over here on the right, no matter how many terms, how many binomials you'll have, eventually, no matter what you plug in, all the binomials will be positive. Then as you go to the left, as you cross one of your critical points, one of the values or binomials will become negative. As you cross the second critical point, the second one will be negative, etc., etc., etc. So what always happens in these cases is the overall value goes positive, negative, as far as you wish to go, for as many binomials as you have. As a final step here in this step, I'd like to show you how to write this solution. If we say all the values where x is greater than or equal to 3 would be with a bracket all the way up to infinity, which of course would have a parenthesis. All the values that are negative all the way up to negative 1, I would list that answer as all the values greater than negative infinity all the way up to and including negative 1. Now, again, to be totally accurate, you probably should put a union sign in between these two, but to be honest, I am going to totally accept that if you just list both of these on the test and tell me that that's the solution to the problem. Let's talk a little more about what I was talking about at the end of the last example. Let's assume that I have a huge number of these binomials multiplied together. In this case, let's just assume I have 6 of them, and I want the product of all 6 of those to be greater than 0. First of all, I would like you to notice that the key is to figure out where they're equal to 0. First of all, at x equals 10, this first one would be equal to 0. The second one would be equal to 0 at x equals 8. The third one at 6. The fourth one at 4. The fifth one at 2. And finally the sixth one over here at negative 2. Now, in this case, I do not actually want the values that are equal to 0. Since they're not included, I will draw open circles at each of these points because these points are not included. What I want is where they are all greater than 0. Well, that will happen when I'm over here on the right. All 6 of them will be greater than 0. So over in this area, it will definitely be positive. The product of all 6 binomials, that is, will be positive. When I cross one of these, this last one is now negative. If I really tried a 9, for instance, 9 minus 10 would be negative 1. The other 5 are still positive, but I now have one negative, which makes this negative. As I cross the next critical point, this next one, say it's 7, would also be negative. So is this one, don't forget. So what I have now is 2 negatives, so again this would be a positive. Continuing this to its logical conclusion, 3 negatives, the product is negative. 4 negatives, the product is positive. 5 negatives, the product is negative. And finally 6 negatives, the product is positive again. So anywhere over here in this area at the beginning will be positive. So those values are all included. These ones are not because it's negative. These ones are because it's positive. These ones are not because it's negative. These ones are because it's positive. not because it's negative, and are included because it's positive. And actually this time I have quite a number of sets I need to indicate. This value would be everything from negative infinity up to, but not including, negative 2. This set would be everything from 2 up to, but not including 4. This set would be everything from 6 up to, but not including 8. And finally, my last set over there would be everything from 10 up to, but not including, positive infinity. My last example was yet a little bit different. You'll notice it's actually almost 3 equations, or at least there's 2 inequality signs. I'm not going to treat this any differently, but instead of doing the same thing to 2 sides of the equation, I'll do the same thing to 3 sides of the equation. So what I'm literally going to do here first is subtract 7 from all 3 sides. That gives me a negative 12. The 7's cancel, so I'm left with just 2x. And 11 minus 7 is 4. Now again, my goal is to get the x by itself, so what I need to do is to divide through the equation all 3 sides by 2. I now have negative 6 is less than or equal to x, which is less than or equal to 2. Let's go ahead and graph that solution. First of all, I've got something going on down here at negative 6 and something going on up here at positive 2. At negative 6, I want the equal to negative 6 value, or the negative 6 value, to be included, so I'm going to put a dot there. At the positive 2 value, however, it is not included. I want the ones that are less than 2, but not equal to. So this dot will be an open circle. Now first, again, I'd really like to double check to make sure these values are right, so let's plug them in. Let's try the negative 6 first. 2 times negative 6 is negative 12, plus 7 does indeed equal my negative 5. Let's plug in the 2. 2 times 2 is 4, plus 7 does indeed equal my 11. So these are indeed my critical points. You could test all 3 values if you want. In other words, put in a negative 7, a 0, and a positive 4, let's say, picking a value from each of the 3 sections to make sure. But what this literally is saying, if you think about it, is I want all the x's that are greater than or equal to negative 6 and less than 2. Well, on the graph, the only values that are greater than 6 and less than 2 are those values right in between the 2. In fact, in most cases, you can simply look at that as 6 is literally being in between negative 6 and 2 and draw your graph accordingly. Now let's, one more time, list this in interval notation. In this case, the negative 6 is included as one of the solutions, so I use a bracket, comma, my upper limit is a 2. It is not included, so I use a parenthesis, and there I have my interval solution.